All right, so there was another question about box transformation. Is there a way to find which transformation is used? Is it possible to force a specific transformation rather than letting the function decide? So yes, and kind of. So here's the recipe we were just talking about. And what I'm going to do is I'm going to make it available. And then I can prep it. So when I prep it, it estimates everything. And then what we typically do is we wrote tidy methods for all these step functions. And, for most of them, like step interact doesn't really give you back anything terribly meaningful because it's not really estimating anything. But step box cox, what it will do is it will return the coefficients that it used to estimate the transformations for these variables. So if I just run that and then tidy the first step, then what I get is that lot area was something kind of close to a log transformation. General living area was definitely like logged. So that's kind of what happened. This is pretty close to 0 to be like, if not the same as log transformation, pretty close to it. So again, if you run the tidy method on these things, like it'll tell you things like what variable levels were in the dummy variables and things like that, depending on which step you run them on. How do we manually transform? For box cox, there's nothing. We estimate it. So even if you found a way to pass it in here, it will be overwritten. A lot of these things that are in the step functions are populated once it's prepped. So it says in the documentation, like, if you modify this, it will be overwritten when we prep and things like that. It's generally speaking a good idea not to mess with that stuff. So there's no way with like box cox that you could prescribe it to be a coefficient of like, 0.25 or whatever. One thing you could do if you really wanted to is you could do, let's say it were the inverse square root. So that would be a coefficient of -0.5. So if you wanted to actually make that happen, or if you knew that that's what it be, what it could be, you could do step mutate, which is a general purpose step that you could do something like lot area is equal to lot area like 1 divided by square root of lot area. So if you want to manually transform things, you can do as many of those as you want to in step mutate. This will always apply it, to the data at any point. So you can do things like this. But there's no way to take, like, let me copy this out. There's no way to tell the box cox what it should be. Oops. Let me fix this.
I think it's worth, when you talk about step mutate, asking just to think carefully about, are you doing something that is like data pre-processing and step in the sense of like feature engineering that you want to learn from training data and apply to test data, or is that something that maybe should be like moved out of a recipe and into your like data pipeline ahead of time?
Yeah.
So that's kind of worth thinking through, I think.
I mean, arguably, yeah. If it were me, I think I would want to do this outside of the recipe. The only time I might not want to is if it's specifically related to something in the recipe. I might want to have it in here. So there's no real difference between you having step mutate in here or mutate ahead of time. If it's a predictor, there's no difference between doing it ahead of time versus in here. So if it's something you always do, like, then yeah, do it outside of the recipe. But if like you're doing this only for like specific model and you want it to be like documented here, for lack of a better term, then it might be advantageous to include it in here. One other thing about step box cox that that just popped into my mind is there's something else. So one problem with the box Cox transformation is the data has to be non-negative. So if you have any negative values in your data, you can't use the box Cox, but you can use this thing called the Yao-Johnson transformation. And step Yao-Johnson is, excuse me, it's step box Cox, and you can use it for any values. So if the data are negative, the Yao-Johnson transformation works almost exactly. The results are almost exactly the same as box Cox. So like the same type of transformation. It just allows you to do it with data that's negative, whereas box Cox doesn't. Excuse me. Okay. Okay. So back to the notes. So we had this recipe. So how would we use this with like a model? So what we would need to do is when we're building our model, we would prep the recipe, then juice it to get the training set, and then put that data into the fit function. So what would that look like? So we would prep the data. You notice there's no training here. So if I want to use the same data that was given to recipes originally, I don't have to say training equals something. And when I ran this originally, it had the training set in it. So I can just prep it here. Now, this is the parsnip model that we made yesterday. That's the model specifications here. Remember, we talked about using fit. So we would give it the juice data. So this is the processed version of the training set. But with fit, we still need to tell it what's in the model. It doesn't know what the recipe knows in terms of what the outcome is and what the predictors are. So you would just say sale price tilde dot, and that would say take the processed version of the recipe, and everything besides sale price is a predictor. Excuse me. And also note that sale price is already on the log scale. So then, we get our LM fit. It's much, much better than the first one we did. It's the R squared is like 80%. And that's our model fit. And then when we want to get new predictions, let's say on our test set, we first bake the data and give it the test set. So this will process the test set. One little thing that I added here is I added all predictors. It turns out that for juice and bake, you don't have to return the entire data set. So it defaults to everything, like literally the dplyr everything function, but you can add in selectors after the data if you only want a subset of them back. And since I'm making predictions, I don't really need the outcome data. So I just said, give me all the predictors, and then I could run that through the predict function. So if you were using sort of like quote unquote manually using a recipe with a model, to build it, you'd have to go through the sequence of prep, juice, fit. And then to make predictions, you have to do this bake and predict. And we realized early on that this isn't awful, but it's not really optimal. We did mention that a lot of models have their own specific, pre-processing. So, I thought early on that, man, it might be confusing if you've built and iteratively tested let's say 5 or 6 recipes, and maybe you tried them across 4 or 5 models, and you've got around 10 R objects laying around, and you got to remember, wait, which one did I use with that K&N model? So there's no connection between this LM fit object and this recipe. So you just have to remember that this is what was used with this. And I thought that's a really bad idea. And there are some more methodological reasons. I thought, well, it's maybe not great to have the recipe and the fit not, cohesive in any way, not coupled. And so, we think about that modeling process. We want to have all the pre-processing that we do for the data and go into the parsnip model. This should be inside that modeling workflow that we talked about yesterday. So, we do want to package these things together, not only for practical reason, but from a methodological standpoint, it's a good idea to couple them together. And so that's where this idea of a workflow is born out of, is what a workflow allows you to do is it allows you to bind together pre-processing and modeling objects together. So they're in one object, a workflow object. And then it also has some nice shortcuts where You don't have to like manually do prep juice fit to build, and you don't have to do bake and predict. So let me show you how this would work. You know, we have our recipe that has not been prepped, and we have our linear model specification. We start out a new workflow just by initializing it, and then we could add the recipe and add the model. It's like that simple. It's just that simple. And then when we print it out, this is before we prep or anything like that. You know, it tells us what the steps were, and it tells us what type of model this is. So it encapsulates both of them. Now, the cool thing is when we go to fit this model, instead of having to worry about prepping and juicing and things like that, I can just say fit, and it does all those steps for me. And so I don't have to worry about where do these objects live, how are they connected together, which ones did I use. You don't have to worry about, right, I need to prep and juice and not bake and prep. It just all handles it for you, and it keeps it all under wraps, so you don't have to worry about things getting disorganized. And then similarly, when you're going to make predictions, you just give it whatever data you want to make predictions on in the fitted workflow. You don't have to worry about baking and predicting. You just run the predict on the workflow, and it gives you the results back. So the workflows are a very nice, like one-step thing you can do. And again, it encapsulates both the pre-processing and the modeling bits together. If you don't use a recipe, instead of add recipe here, if it's something as simple that you need a formula, you can say add formula and be like sale price tilde whatever, and add the formula in here. So you don't have to use a recipe. You always have to have a model, but in terms of a preprocessor right now, you can have a recipe or a formula. So that's nice. You might fit a model and decide like, oh, yeah, I need to increase the number of spline terms because 5's not really, I think I can get better performance if I make it like 10 or 20. So you might redefine this recipe, and instead of like creating everything from scratch, we do have like an update function. So you could say like update recipe and give it a new object. Or if you just want to get rid of the recipe and use a formula, you can, you know, remove different aspects of these things. So that's nice. A secondary thing, we're working out the API for this a little bit. And you'll see this in my talk next week, where I talk about like multi-level, like mixed models and things like that. There are times where you want to do your pre-processing with a recipe, but you need like a specific type of model formula for the model. And that model formula might not be something you can give to model.matrix. So when I talk about like random effects models or tidymodels, the formulas that you use for, let's say, a stand model or for like a LME model have things in the formula that are related to the statistical parts of those models. And if you take that formula and give it to model.matrix, model.matrix fails. So we're going to have a better way of doing this, but there's sometimes when you add the model here, you can add another formula here that is specific to the statistical model that's going to be used. So we're gonna talk about this not that much more in the course notes, but this is something we're working on a lot, and we'll have some blog posts and training materials on exactly when and how you would do that. So it's working now, and you'll see that when I do my presentation. But it's not the API, the interface that the users use is not quite the way I want it. So it'll be changing a little bit. So basically, the formula makes your life a lot easier. You do a little bit of work up front to bind these things together, but when you go to use them, it becomes much, much easier to use. So that's the main point of workflows. You'll see them more as we go throughout things. Any questions about that? Okay. So this is a little bit our technical stuff here. It's very important, and it's something that we've spent a lot of time on in the last few months, is we want to talk about how you encode predictors, and especially what the underlying model does and wants versus what like a recipe or a workflow or a parsnip model do. So the thing is, the good and bad in R is there's a lot of heterogeneity in interfaces, like I talked about at the beginning yesterday. Like, you know, sometimes or most of the time you get dummy variables from a formula, but sometimes you don't. There are things like the main SVM function that we advocate. Instead of doing like the regular dummy variables, it uses the one hot encoding method, which isn't a problem, and it's probably the right thing to do for them, but it's just a little bit different than what your standard formula method would do. There are cases where Parsnip does some of that work for you. So Glimnet, for example, is a model we'll look at in the regression section, and it does not have a formula method. So when you give a Parsnip model a formula, what Parsnip does under the hood is do the model.matrix stuff for you and hand it off to Glimnet. And so what we've tried to do is, since there's a lot of variability in what the underlying packages want and would do if you gave the data to them directly, what we've done is in workflows in Parsnip, what we've tried to do is emulate exactly what the underlying modeling package would do. So for example, if you just use like a formula method with a workflow, workflow would look and say, oh, what would XGBoost do? And then it will mirror the sort of like predictor encoding methods that XGBoost wants. Or like if you gave it a random forest model, workflows would look at that and say, oh, right, it's random forest. They don't want me to make indicator variables, so I'm not going to do that for you. And this is all related to what you would do with a formula. It wouldn't do that with a recipe, but the formula method has to make some choices about what the data should look like. You have full control of what a recipe does. But when you use a formula method with a workflow or with Parsnip, we try as hard as we can to emulate what the model function would want or need or do if you were to just have been using that directly. So it's a little bit of like inside baseball, and it's something you might not have thought about, but we just wanted to say this because we want to make sure there's no real difference in results between using a workflow or using just Parsnip or just using the underlying modeling method. So, okay. So this is normally works better in person, but here's a quick knowledge check. So let's look at the first one. On the left-hand side are some tasks, and then the right-hand side are some package names. So if you were to fit a KNN model, which packages would you use to actually do that? Does anybody want to say? This goes a lot faster in person. Somebody was typing. Here, I'll give you the first one. Parsnip is the one you would associate with models. So chances are you would want to use select Parsnip for that. You could have said workflows because workflows also bundle Parsnip together, but it wouldn't be like Yardstick. So if you were trying to process the data and extract some holidays from dates, does anybody want to suggest maybe what package that would be? Like what you would use for that? Right, recipes. How about a training and testing split? We haven't looked at that one in a while. Good, okay. Nice, R sample. Good, that one came through. The next one's easy, bundling a recipe and a model. We just talked about that one. That's workflows. Davis added high in vitamin C to this list, which turns out is what a carrot does for you. What would you use to compute R squared, do you think? Yeah, Yardstick. Very good. And then let's say you're going to bin a predictor. So you have like longitude and latitude, but you want to like discretize it or chunk it up. I really don't think you should do that. But like if you were going to do that, like what package do you think you would use to bin that predictor? Yes, exactly. Recipes. So recipes tends to be for like processing of predictor data. So if you were like to bin a predictor, There are some methods in recipes to do that. There's some recipes in embed to do that, but they would all be recipe steps. So there you go. Can I say more about not to bin? I can. And oops, I don't want to keep doing this, but I wrote a whole like book chapter about this. I mean, the name says it all. You find it. It's in here. Discretizing predictors as a last resort. Well, you can read it here about what my arguments are. There are some cases where this will actually give you a better model fit, but I think that's like 5% of the time. I think that keeping numeric data numeric is the way to go. I know I've worked with a lot of scientists who their immediate thought was like, let's chunk it up because it makes it easier for me to put in a pie chart. And I'm not joking. I had a lot of chemists I worked with that we jokingly started having something we called wall of pi, where they would have two predictors that they would just arbitrarily discretize. So they had like a grid, and then we were trying to do classifications. They'd have like 3 classes, and they'd do a pie chart. So they'll have like 10 rows and 5 columns and a bunch of pie charts in there. And they would say, well, it's obvious that so-and-so is really driving the blah, blah, blah. And it was honestly, it was kind of nonsense. And it just is one of these things where like, there's probably more, I mean, from the information theory standpoint, there's way more information in a continuous variable than there is in a categorical variable. So, you know, if your data looks like a step function where it's like off and then on, then yeah, discretize that. But I feel like it's not the best of ideas generally. And there was a really great paper that we link in here that showed that it increases the false positive rate. So if you took a bunch of predictors that are maybe not that informative, when you discretize them, even depending on especially how you do it, could make them seem a lot more important than they actually are. Basically what it does is it has a way of compressing the variability. So when you discretize things, you're like eliminating almost all the variability, and then things look more, these patterns that you see end up overfitting a little bit because you've artificially eliminated all the variation. So there's some simulations that are shown in this chapter, and in this paper here, what was it called? Inflation of correlation, the pursuit of drug likeness. This is a chemistry paper, but it's worth reading if you have access to it, because it's very readable and it does a good job of saying, you know, here are the consequences of doing data analysis on discretized predictors. So I really enjoyed this paper. Is it problematic to use the outcome to lump together factor levels, especially among rare items? I think that's fine. I'd just be very careful that you're not overfitting. So if you don't have a lot of data, I would worry that like a couple of data points might be driving some of those choices. So one thing you might want to do if you're going to do that is maybe use a step mutate. One nice thing about using step mutate is when we resample these things, if there's something that's kind of like speculative like that, you might try to encode it in the recipe using something like step mutate, so that when you resample it, you'll get a good sense of whether it was a good idea or not. We'll talk a little bit about this with the resampling, but things you do outside of the model workflow, if they're bad choices, you very often don't know until you get to the test set. Including them in the recipe or in the model workflow and then resampling them does a much better job of giving you honest estimates of performance. And I mean like honest from the sense of like generalizable estimates of performance. If you pre-do something, a step like that, then you know, resampling, for example, doesn't have the ability to tell you whether it was a bad idea or not. So yeah, I don't think that's a bad idea. Just, make sure you're not over interpreting a small amount of data to do that. Other question. Some data pipelines collect sensitive data that's anonymized prior to being exposed for analysis. Sometimes those routines bin potentially identifiable information. I know this discussion is specific to modeling, but should binning be used as a last resort in a data warehouse? I mean, if you have practical issues, like maybe regarding data size or something like that, or identifiability, then sure. I mean, if that's what you have to do, then do it. So, I mean, I wouldn't say that don't ever bin, but my chapter title there was like binning as a last resort. It's not something I would do automatically unless I had a really good reason to do it automatically. So yeah, if you need to do that for anonymization, I think you might be losing some performance, but if like that's the necessary thing to do, then yeah, like go ahead and give it a shot. That would be my suggestion. Let's see. Our workflow is a single model, or do they encompass multiple models for comparison? It is a single model. Yep. One recipe, one model is what is inside a workflow. Yep. Okay. All right, so that is part 3. Let's go ahead to part 4. I try to prognosticate whenever I teach this course as to whether we're ahead or behind. And I find that when I say it out loud, I end up being wrong. I feel like we're a little ahead, which is okay. As long as I'm not going too fast, then I think we're okay. But I think we may be a little bit ahead of what we would normally be, where we would normally be at day 1, which is not a big problem. Okay, so now what we're going to talk about is we're going to talk about resampling methods, and then we're going to talk about model tuning a little bit along with something called grid search. So we won't get through this chapter. It's like 48 slides, but we could probably get started on resampling and then show that in action next Wednesday. All right, I think it's the last chapter where we use the AIMS data. So if you're sick of this data, this is the tail end of it. Here are all the things that we're going to use going forward from previous slides. So just, when we do things, this is what we'll need. All right. So what resampling is it's a sort of like an empirical simulation system. And it sort of emulates a little bit of like what we're doing with a training set and a testing set. So if you think back to what we do with training and testing, we wanted to compartmentalize the data that we use, the data that we use for model fitting. And, the test set was something we wanted to hold back that was not used for model fitting that will give us like a really good generalizable answer to what is my model performance. If these two data sets were mixed together, then, the estimation of model performance will really be biased because that data was used for development and evaluation, and that's problematic. And so what we've been saying over and over again is like, yeah, we're using the test set, but like really don't do that. So the question is, well, wait, if I can't use a test set, what am I supposed to do? And the answer is you're going to use these resampling methods, and you're going to use them on the training set. So for most cases, we do like a testing and a training split up front as our initial split. And then resampling methods are done only on the training set. And you would do multiple iterations of resampling. And those kind of emulate it where we're going to take some data from the training set and use it to build the model, and then some of it to assess performance. And so I'm going to change my lingo here a little bit. Like if you read like Stack Overflow posts about resampling, they talk about like the training and test set. I want to reserve the term training for my initial split of the data. That's not the test set. So when I say training and testing, I mean that initial split that we used to take some data out for testing and everything else is for training. And then within resampling, the terms I'll use is the analysis set is very much like the training set. It's within a resample, it's the data you're going to use to build your model. And then the assessment set is very much like the test set. We're going to make predictions on it to assess model performance. Okay, so we're going to do this over and over again. We're going to take the training set and we're going to do some sub-splitting on it repeatedly. And then from that sub-splitting, we can get good estimates of model performance without going to the test set. So that's the general strategy here. Is we're doing sub-splitting on the training set only, and that will help us get good performance measures. So let's talk about like how to do that. There's a bunch of different ways you can do resampling. Here's a link to the book that has some of them, and you could read more about them there if you want. So again, to talk about data usage within resampling, what happens is our analysis data is the data that is used to build the model, and a recipe could be in here, so it would be like the pre-process data and build a model, and then that results in the fitted model. So the sort of like yellowish orange here are all the parts that are affected by the analysis data. Then we apply that model to the assessment data and get our predictions, and then compute, let's say like RMSE or R squared or whatever we want to from the performance, from the assessment set. Okay, so again, analysis data is like the training data, fit our models, do our pre-processing with that. The assessment set is very much analogous to our training set that is only used for measuring performance. And that's how data are used within resampling. So we're going to talk about different resampling methods. Mostly they are different in how they separate out the analysis data from the assessment data. There's a variety of ways you could do that data split. So those are the differences between different resampling methods. The one you've probably heard of the most, sometimes people call it k-fold cross-validation. We're going to call it v-fold because we talk about the k nearest neighbors model, and I didn't want to k versus k sort of thing. So v-fold cross-validation is something where you take your data, and let's say v is 10. What you would do is the diagram says 5, so let's use 5. So if v were 5, what you would do is you would randomly allocate all of your training set data to 5 groups that are about the same size. So you could use stratified random sampling, you could use regular old simple random sampling, but you would randomly allocate, let's say for Ames, our training set is like, I think it's like 2,100 data points, I think. You would randomly allocate those data points to 5 groups that are about the same size. And those are called the folds. So if v is equal to 5, and we have these 5 sort of virtual groups that are made through random sampling, we'd have 5 folds. And so on the first iteration of v-fold cross-validation, we take the first fold out, we fit the model on 4 out of the 5 of them. And then that model gets used to predict the one that we left out. So on the first iteration, we have about 1/5 of the data that is used to measure, let's say, the root mean squared error. So at this iteration, this block of data generates us 1 root mean squared error. And that's iteration 1. Iteration 2 takes that data, puts it into the model with folds 3, 4, and 5, and leaves out fold number 2. And then you fitted a model on a different, slightly different 4/5 of the data, predict the held out 5th, and that gives you an RMSE value. And you keep going round robin till at the end of this, you have 5 separate RMSE values. And those performance estimates are based on different data sets, right? They're not used for, no one of them was shared data with the modeling data set it's corresponding to. So you have like this N of 5 for your performance metrics. And it turns out that averaging those resampled estimates of performance give you a very generalizable error estimate that tends to track with the test set. Depending on the data set and things like that, in my experience, that they tend to be pretty well correlated. So, so what we've done here is repeatedly 5 times, we've done like little mini training and testing sets. And all of our test sets are, we're calling them the assessment sets here, are really mutually exclusive from each other. And our overall estimate of performance is the average of the 5 performance metrics we get for each fold. Okay, so basically, if we were to take our linear model that we just looked at the end of the last session, we would generate 5 different versions of that linear model based on different resamples, and each one of those has its separate RMSE value that we would average. And the average RMSE value there is our estimate of how well that model does, like the overall model. How would you apply v-fold cross-validation to time series? I will talk about that in a minute. I'll talk about time series in a minute. As a rule of thumb for the number v, I'm a purist. I think 10 is a number. You have to have a pretty good reason for me not to use 10. Some people use 5, others use 10. There's a trade-off, and I've written a couple of like excruciatingly long blog posts about this. The difference between 5 and 10 is about variance and bias. So the thing is, as v gets smaller, your holdout data gets larger. And as that happens, the bias gets bigger and bigger. So the bias is, if my true RMSE for a model is 0.1, the bias is sort of like, what am I shooting for? So if I have a pessimistically biased model, even if my RMSE is 0.1, it'll probably estimate it always on average to be off of that. An unbiased estimate would always be sort of like trying to shoot for the target of 0.1, even though it doesn't know what that true value is. It's an unbiased estimate is something that is like kind of like shooting for the right thing, whereas a biased model is shooting for something that's slightly off target. So that's what the sense of bias is. The problem is, as v gets larger, the bias goes down. The problem is the variation goes up. And so in many parts of statistics, there's this thing called the variance bias trade-off. And in this particular case, lower values of v, they're faster, computationally faster, because you're fitting less models. But at the same time, the variation with those is better, but their bias is really bad. They tend to be very pessimistic. So like if your true accuracy is like 90%, you might be estimating it to be like 80 or 75 or something like that. Whereas if you did like v equal 10 and your accuracy is 90%, you'd be shooting for something much, much closer to 90%. So it's this trade-off of like computational time and how much variance and how much bias to deal with. So I tend to, and this will answer another question that just came up. What I tend to do is I tend to use v equal 10 and then do the calculation of like, all right, how much data is my training set? So if I have like 2,100 properties for AIMS, a tenth of that's being held out at a time is about 210 data points. Do I think 210 data points is enough data to, let's say, estimate an RMSE? And that's like how I think about, is the variation going to be too large or too small? And I think 210 is probably be pretty good. So an average of means of size 210 for me is just in my head doesn't seem bad. I think that's a pretty good. So for me, like v equal 10 there doesn't seem so bad. But let's say my training set was 200, right? I'm holding out 20 things. Maybe like, ooh, the variation around like RMSEs of 20 data points is maybe not that great. So here's the thing, is you can solve the problem of variation very easily. And what you can do is you can do something called repeated cross-validation, which I'll talk about in a second. And if you're averaging more things, if you're averaging more than 10 things, the estimated variation gets closer and closer to the real thing. So you can solve the problem of extra variation with replication. You can't solve the problem of bias with replication. So if I use v equal 5 and that's very biased, it doesn't matter how many times I replicate cross-validation, that bias is baked into the cake. Whereas I can solve variation by basically like increasing the sample size. Excuse me. So if my training set is 200 and I feel like tenfold would hold out 20, and that would probably give me a pretty noisy estimate of performance, what I could do is I could do, let's say, 5 or 10 repeats of cross-validation. So if I do 5 repeats of tenfold cross-validation, it does that same tenfold cross-validation allocation 5 different times. So it's like blocks of 10. And instead of averaging 10 things at the very end, I'm averaging 50 things at the very end. And that's more computation, but that will drive down the variation in my performance estimates quite a lot. And again, you can't solve bias that way. So like increasing the number of folds or increasing the number of replicates of cross-validation mostly is a problem for computational time, because now things are going to take 5 times longer than they would have with tenfold cross-validation. But my feeling about that is that's just like CPU cycles. I would rather spend more time computing and like go out and walk the dog or something than to do less computing and have to live with really noisy parameter estimates. So that's kind of my feeling about that is, yeah. So as an overall summary of all that stuff I just talked about, I'm pretty diligent about always using 10. I think 10 is the right number. I've done a lot of simulations and a lot of stuff, and I feel like 10 is a good number. If I do those calculations in my head about like divide by 10 in the training set and how noisy is that, I will solve the problem of noise by replicating cross-validation. The last example data set that we'll use for classification only has I think it's like 250 data points in it. So we're going to replicate tenfold cross-validation in that, just to show you how that works. Cross-validation is probably the most popular resampling method. Its properties are generally good. It's easy to implement, and overall, I'd say it does really well. The things that I will show you, for example, if I had 50 data points and I do tenfold, if you look across rows, every training set data point only ends up in one analysis set. I'm sorry, one assessment set. So you don't have like the same data point being in multiple holdouts with a single repeat of cross-validation. Now with 5 repeats, that same data point will be replicated across 5 different assessment sets. And that's not the end of the world, but at the same time, I think one of the reasons that cross-validation works so well is within a single repeat of cross-validation, you're not reusing the same data points for assessment. So that's a nice feature of this thing. Any more questions about cross-validation? We're going to use it quite a bit, so you might have more later on. Okay. I thought I did it here, but we will talk about 2 other resampling methods. We'll talk about the bootstrap in a little bit. And I thought the time series stuff was here. I don't think it is. It's in the next section. The problem with using k-fold or v-fold, cross-validation with time series data is if you're just randomly sampling data, you might be kind of handicapping your model data by breaking up the trend data, right? So there are a lot of specialized methods for resampling time series data. We have them in RSample. We'll be talking about one later. The main one that I've used is called rolling origin forecast resampling. I'm sorry, rolling forecast origin resampling. And we'll demonstrate that in a little bit. It's not the only method for resampling time series, but it's the one that I think people consistently use. That is, now I think about that, is in part 5. But we'll have an example time series data set in the next section. So you'll see that in action. Okay. So how do we do this? One thing that often is a question that I'll address here is if we're doing just like one repeat of tenfold cross-validation, we generate these 10 different models that we use to measure performance. Like, a common question is like, well, what happens to those models? Basically, we throw them out. The models that we use during cross-validation are only used to estimate performance. So it's not like some funky ensemble method or anything like that. We're only using them for that purpose, and then we can just get rid of them after that. We don't really use them after that. So if you're doing this with RSample, we have a function called vfoldcv. You give it the training set, and then like we did with the initial split of the data, you want to set the seed to make sure that your random numbers are reproducible. By default, it does tenfold cross-validation. And what you get when you run this is you get this weird looking tibble. So it has as many rows as there were splits of the data. And so if you're doing tenfold, you have 10 splits. And there's 2 columns. One's called splits and one's called ID. The ID just tells you it just says like fold 1 through fold 10. It's just like an identifier column. There's nothing magical about that. What this split column is it's the same type of object we saw when we did the initial split, where it has the allocations of which rows in the original data go into into the analysis set and which rows go into the assessment set. So it's its own type of object that we could use, just like we did when we did our training test set split. And then it's in a list column. So these are lists of objects that we can use. So let's look at how we can use them, like on an individual basis. But the point I want to make is the results of all these RSample resampling tools, these functions, always produce a tibble with splits and identification columns. And then we'll show you how we use them. So let's look at one of them. So if we just take that column and get the first one, this might look similar to what we saw with initial split, right? It says analysis, assess, and total. So the total here is our training set size. The analysis set is how many data points were in the 9/10 of the data and how much was in the 10th that was held out. So this would be the size of our analysis set. This is the size of our assessment set. And this is the original training set size. And so if you remember, when we did our initial split, we created that split object. And then to get the training set, we ran a function on it called training. And that gave us a data frame back. And then when we ran the function called testing, that gave us the data frame that is for the test data set. So very, what you would expect is we have functions called analysis and assessment that when I run analysis on the split object, it gives me the data frame back with these rows. And when I run assessment, it gives me a data frame back with these rows, just like we did before. So it basically is a tool for getting the subsets of a data frame for that particular resample. So let's look at a nearest neighbor model. We've been looking at linear regression, so let's just for kicks look at like a 5 neighbor model. So what a 5 nearest neighbor model would do is it would, if you were trying to predict this data in Ames, and let's say we're only using longitude and latitude as our predictors, it would literally say, well, who are my 5 closest neighbors? And then it would get their sale prices and then average those to make the prediction for this sale price. So for example, let's say we're trying to predict this one over here. It's obvious what the 2 closest neighbors would be, but some of those neighbors might be pretty far away. So we'd look at the 5 closest neighbors regardless of how near they actually are, and then use those data to make predictions on what the new sample is. I'm waiting for a question. Don't rush. I'm just saying if anybody's wondering why I stopped talking. All right, I'll catch up to the question in just a minute. So write it out, but I'll come back. So if we were to fit this k-nearest neighbor model and want to estimate performance, like how would we do that using that R sample object that we just created? Well, the first thing we need to do is create a parsnip object for the model. We talked about how to do this yesterday. For KNN, we'd use the nearest neighbor model and say 5 neighbors. The engine, if you might recall, in this case is the package that we'll use, which is called the KKNN package, which is pretty good. And then you could use KNN for either classification or regression models. So we have to tell it, yeah, we're doing regression, so predict a numeric outcome. We can make a workflow out of that. So we say, bundle up that KNN model, and we'll just use longitude and latitude as predictors to predict sale price, which, as you remember, is already on the log scale. So if we were to just fit that KNN model, what KNN actually does is it takes the training set, which is like, let's say this big white set of data points, and it just stores it, right? So it just stores the data that it needs. And when it goes to make predictions, it looks up which parts of that training set are the nearest neighbors and then pulls out their outcome data. So for KNN, there's not really any like model fitting per se. You're just storing the data and then looking up the data set when you go to make predictions. So if we were to do this, how would we do it? Okay, maybe I'll answer this question really quick. Question is, will you be talking more about cross-validation in its relation to a separate validation set with respect to hyperparameter tuning? Many practitioners use assessment or separate validation set for early stopping, etc. Also, how then does this relate to dataset reuse? Yeah, that's a good question. I tell you what, here's what I'd like to do. I have answers to all those questions, but we have like 10 minutes. So I'm wondering if I should answer that question or if I should go through this. I tell you what, here's what I'm going to do is I'm going to stop here for slides, and then I'll answer this question, and that's where we'll end today and pick up this this bit when we come back. So, okay. So there's a lot to unpack in the question. Will I be talking more about cross-validations relation to a validation set and tuning? We will definitely be talking about model tuning in this section, in this slide deck, and how to use it with resampling. So we will talk about that. When it comes to a validation set, you can do that in tidymodels. It's actually really easy to do that. The way we do it, I think I have a diagram in here. Let me find it really quick. That shows how we treat a validation set. Let me find it. So some of you might be asking, like, wait, what's this validation set he's talking about? Validation sets are when you set aside a single like resample of your data. Like we see this a lot of time in deep learning where they have oodles and oodles and oodles of data. And what they'll do is, or let me not share that quite yet. What they'll do is, they have like 1 million images, and they might set aside like a set of 1 million that they can, when they do their model tuning and things like that, instead of doing like 10 holdout sets, they'll do like 1 holdout set, which is large enough to be accurate. And they'll just keep checking the results against that 1 holdout set, which they call the validation set. So validation sets are really good when you have a lot of data. Basically, if you had like millions of data points, I would not recommend necessarily doing 10-fold cross-validation, because the uncertainty estimates, like the noise in holding out 1/10 of a million data points, is low enough where that ought to be enough to get good performance estimates. So, so the way we think about resampling compared to a validation set is, here's where the schematic comes in, is a lot of times people think of things as like, I have my data, I do initial training set, I hold out some validation during the model development process, but then I have this separate testing set. So they're both colored kind of purple here because they're both used for making different assessments of performance. and the training set is being used for all the model development, much like we were doing before. So the way that we've structured it in our sample is we treat the validation set like it's a resample, but just with one iteration of resampling. So what we'll do is we'll take, instead of like having a three-way split here, we'll do two binary splits and say, here's our test set, here's the data that's not in the testing set, and then partition that into training and validation. So functionally, it's not really any different than what we've been doing. There's a function in our sample called validation split. And so if I did that on the Ames, well, it says train, but like on the Ames data, I get a single split back. And you can say how much you want to hold out for validation. By default, it's a quarter. And it's just like resampling, but it's just like one iteration of resampling. So rather than us writing different wrapper methods for a separate validation split, it's effectively the same thing to say, well, it's like resampling, but we just have a single split. So at the end, when you compute your performance, you compute it once, and you're not averaging anything like you would with tenfold cross validation. So essentially, we treat it like a single iteration of resampling, which is fine. That works fine. So I mean, historically, the validation set came out of the neural net literature from like the 80s, and what they were finding is when they were fitting their neural networks, they were trying to figure out like how many like epochs to fit the neural network on. And what they were doing originally was they were just repredicting the training set. And a neural network can very easily overfit to the data. So what they found was the longer they trained the model, the training set error rate went down. But if they compared that to a separate data set, eventually that error rate would go up. And so then what they said is like, well, okay, we need a different way to figure out when to stop training. So we're going to not use a test set. We're going to split off another set of data to use as a validation set, and that will be evaluated at every iteration of training of the neural network. And then we'll stop when we see that validation error start to increase instead of decrease. Because the training set error will always decrease, whether the model is doing a good job or not. So they're overfitting to the training set. So that's the original like way the validation split was devised and how it was used for a long time, and kind of is still how it's being used. And you can do that with tidymodels. You totally have that ability to do it. For example, if you were looking at single layer neural network, it's also called a multi-layer perceptron. You would use the MLP function, and there's a tuning a parameter you can tune for the number of epochs, the number of iterations. So I'll show you how to tune things in a little bit, but using a validation set or tenfold cross validation, you can tune the number of iterations of training to use. So for me, it doesn't really matter whether you use tenfold or validation. You can use those resampling methods or those validation methods the same way. They're kind of the same thing. It's just whether you do one of them or 10 of them or however many you want to do with them. So functionally, how they get used in like the tuning process is kind of the same. So that would be my answer to most of those questions. How does this relate to data reuse, producing optimistic results due to reuse? So we generally, the way tidymodels is set up was like 99% of the time, we don't have any reuse of data. So we always calculate performance metrics using data that was not used for modeling. So we protect very much against reusing data for multiple stages of modeling, like modeling versus performance estimates. So we're pretty dogmatic about that. The only exception to that is the problem is, let's say we're tuning the number of neighbors in this model, which is what we're going to do next Wednesday morning. We use the resampling results to say, oh, I think like 7 is the right number of neighbors for this model. And then what we do is we take the RMSE associated with 7 neighbors and say, oh, that's what we think our model performance is. There's a slight problem with that because we're using the same data to optimize the model and estimate performance. So theoretically, there's some optimization bias there, that the bias in our performance estimates might be slightly optimistic because we're just picking the best one and saying that's performance. There's a way to get around that by doing something called nested resampling, where you embed like a resampling method within, let's say, each of your 10 folds. And that's one of these levels of resampling is used for optimization, and the other level is used for quoting what the performance is. And there's been a bunch of papers written about this. They're right. There is such a thing as optimization bias. The problem is twofold. The problem is when you do nested resampling, you sort of multiplicatively increase your computational time. So if something takes 10 hours, it's going to take 100 hours to complete before, because you've added at each resample, you've added another whole layer of resampling inside of that. So computational time, I normally would tell people to be like, well, don't worry about that. Computers get faster. The reason why we don't really rely on nested resampling all that much is I've been thinking about this for a long time, and over like the last 20 years, I have never found an instance where that very real bias, like it's a real thing, is large. So there are some data configurations where you can prove that that bias is real. But for me, and I've looked at this like a lot, I've never found that the amount of bias being larger than the experimental noise. So for me, it's always been small enough where I can barely detect it. So it doesn't really have like a appreciable negative effect on the process of modeling. Now, there are going to be exceptions to that, but I've looked and looked and looked and looked, and I've yet to find situations outside the ones that have been published, which are not really all that common, to say like, wow, I really got the wrong answer by doing, by not doing nested resampling. So I think it's a real problem, but I don't think it's a problem that happens in practice enough to where I would want to multiplicatively increase my training time. So I think it's the right thing to do, but not worth the effort outside of a couple of circumstances. So that's the only place where we're not very dogmatic about data reuse, because I just honestly don't think it's worth it. Apart from that, we are really good at making sure the data does not get reused anywhere. So yeah, hopefully that answers your questions. Okay, if you want to follow up on that, or if anybody has more questions, go ahead and add them to the general channel whenever you get a chance. I will stop here, and we will start on model resampling and model tuning next. My voice is starting to go next Wednesday. So we'll rejoin here in 6 days and start from there. Again, Slack any questions and we'll answer them. Jared or Ahmad, anybody want to say anything?
Yes, so hope everyone had a good day of the class. Again, I will laud Max a little bit, saying that I saw this workshop not too long ago and he's already made changes, so it's ever evolving. And luckily not breaking changes, just new changes to the content. And as Max said, we will be rejoining together in about a week from today, a week from yesterday, I guess. After everything has a chance to sink in, you get a chance to think about it. We will come back next week for parts 3 and 4, I guess parts 1.5 and 2. I'll have to think about how we're going to call that. And we'll be back for that. So everyone, same idea next week, but we'll be sending you a new Hopin link. The one we're using today and yesterday is going to expire, and we will have a new one for next week. So check your email for that. If you have any feedback, please send it to us. Please ask questions of Max, Julie, and Davis. If you have feedback about the platform or anything else, let us know. That us being the Lander team, we handle all the logistics. We'll take care of all that. And I look forward to virtually seeing everyone next week. And remember, those of you coming to the conference, I think most of you have also signed up for the conference. Remember, it's going to be 2 days of talks, and we actually have a lot of fun activities planned for the happy hours. It is BYOB, but we're actually working on a way to help you have that too. So I hope everyone has a good week, and we'll see you next time. Thank you, Max. Thank you, Julia, and thank you, Davis, who had to
Thanks.
slip out.
See you next week.